So my name is Allison Leidner, and I work with the NASA Earth Science Division. And specifically, I work with our Biodiversity Research and Ecological Forecasting Applications programs, which are programs that directly fund researchers and decision support projects to help understand biodiversity here on planet Earth and also inform conservation activities. And so just as a note, at our headquarters activities is where a lot of our funded research happens. So I'm going to be really talking to you about NASA from a programmatic level. So NASA is an innovator for earth science and has an amazing set of observations, technology, and research that are at the cutting edge of science. But not enough people are using this for conservation. So what I want to talk to you about here is give you a sense of what NASA does for earth science and what's coming down the road for us in the coming years, and think about how we can apply that better to conservation. So this image of Earth at night powerfully conveys our human impact on the planet. And I know in the bright lights here, it's a little bit hard to see. But as you well know here at the Earth Optimism Conference, humans are the dominant species on the planet. And what the Earth Science Program and what the viewing Earth from space allows us to do is better understand how humans act as a global species and the impacts that this has on plants and animals on the land and in the ocean, and understand how we can better apply that to conservation. And so by taking this global view, by looking at it from the top down, and then working with our partners who look at everything from the bottom up, we can have a better understanding of how to integrate across scales and develop high quality scientific data from a global perspective that can then be used for conservation. So this, there we go. NASA currently has 19, is there any way to dim the lights in this room? Can maybe someone try to take a shot at that while I'm talking? There's currently about 19 Earth observing satellites that circle the Earth. And you can see a variety of them here, and they take different kinds of measurements that are useful. So some of you may know that our satellites are able to look at temperature and precipitation. We can also make measurements of land cover. We can take a look at ocean salinity. We can take a look at productivity on the land and in the ocean. And it's this combination of observations that allow us to get a better understanding and piece all of this information together to understand how the Earth is interconnected, to understand land and ocean and atmosphere. And by looking at these interconnections, we can better use that to inform biodiversity. So what I want to give you a quick primer about first is how our satellites actually work. So our satellites don't just take pictures of the Earth. They collect sophisticated information about the light that hits the Earth and then is reflected back. And that's what our Landsat satellite does. So this Landsat satellite is a collaboration with the U.S. Geological Survey, as many of our satellites have domestic and international partners. And what the Landsat satellite does is circle the Earth once every 90 minutes, imaging a swath of that Earth. And then over 16 days, it visits every place on the Earth once, and we use that to develop an image of what is happening on Earth. And everything on Earth has a different spectral signature. And so when we are able to collect information in different wavelengths, so we can look at the visible spectrum, but we can also look at ultraviolet information, we can look at information that's in the thermal and in the microwave portions of the electromagnetic spectrum, we can actually get a sense of what is on Earth and how is it changing through time. And so it's this combination of information, and Landsat is actually a program that's gone back to 1972. So we have a 40-plus year record of what the surface of the Earth looks like. And this is an amazing record to use for conservation purposes. And the kind of information that we can get is what you see here. Oops, got a little ahead of myself there. What you can see here. And so this is the kind of high quality scientific data that can come from our Earth observing satellites. So what you're seeing here is vegetation on the land, productivity on the land and in the ocean, and you're seeing this through a seasonal cycle. And this data is combined from multiple satellites. And so what's really important here is that we can calibrate and validate our satellites against each other and combine all of this information, again, to provide this really sound understanding of how the Earth system is changing. But at NASA, it's not just about the observations we make from our satellites, it's also about the models that we use. And so we've developed a model called the ECHO model. And this is one of my favorite visualizations. I just think it's stunning. And this model takes satellite data and combines it with data that's collected from the ocean to look at how oceans circulate. And the colors that you're seeing are sea surface temperature. And this model is really great for me because it highlights how interconnected our Earth system is. You see how heat is transported from the Gulf of Mexico to Northern Europe to make Northern Europe warmer than it otherwise would be. Off of the tip of South Africa, you see those gyres that transport phytoplankton and zooplankton, and also transport nutrients from the Indian Ocean to the Atlantic Ocean. And so it's this interconnected perspective that helps us understand what's happening at a local place, because many of you do conservation at a specific place or you work on a specific species. And so understanding the global context for that local place, but then also as we're able to develop higher spatial resolution information, as well as developing information that's collected repeatedly over time, we can also connect that to local places and scale back up. So you can't do conservation without this global perspective, and we can't look at this global perspective without tying that to the kind of information that people collect at local and regional, even continental scales, with information on the ground and in the ocean. So let me give you a couple of examples of what we fund people to do with this data. So in both of these cases actually take advantage of both research and our conservation applications projects. So what you're seeing here is a global map of forest cover that was developed using the Landsat satellite by Matt Hansen and his colleagues at the University of Maryland. And this global forest cover data set is a key component of Global Forest Watch, which is part of the World Resources Institute's new portal to provide information to decision makers in natural resource management. And with this global map, researchers at the Jane Goodall Institute looked at this and said, we can do even more than just looking at using information from where is forest and how is it changing through time. So the green areas are where a forest, and the blue areas are where we've seen forest gains between 2000 and 2012, and the red areas are where we've seen forest loss. So you can see the arc of deforestation in the Amazon and in other places as well. And the Jane Goodall Institute said, we have lots of observations about chimpanzees, and we know a lot about chimpanzee behavior. We know a lot about working with local communities in Tanzania and in the surrounding area, including Gombe National Park. So they all got together and collaborated to do this project with a grant from NASA to look at citizen science data. They armed local citizens with tablets to record where they've seen chimpanzees, when they've seen them. And for example, you can see in this bottom picture on the left is an example of a chimpanzee nest, to develop a more detailed understanding of chimpanzee habitat suitability in Tanzania, and then take that to local villagers and work with them to talk about identifying conservation areas. And it turns out that these areas are not just important for chimpanzee conservation, but because of the long history that the Jane Goodall Institute has in working with these places, they know that it's also important that reforestation efforts can help prevent landslides that affect local villagers in a variety of ways in addition to chimpanzee habitats. So Back to the Ocean is another project led by Helen Bailey and her colleagues at the University of Maryland Eastern Shore. And what they've done is they're concerned about ship strikes against whales, which is a significant cause of death among whales. And what the idea here is that there's a lot of shipping and naval activities off of the west coast of the United States that can hit whales. So if we have a better understanding of where we anticipate whales to be and when, we can avoid them. So they used ship-based surveys of whales combined with satellite data looking at sea surface temperature and sea surface height and chlorophyll to build predictive models. And so this is a screenshot on the bottom from their website just the other day about information from March and April as to where they expected the probability of certain whales to be, and then also how many they expected to be there. And by working with NOAA and other agencies, they can feed this information to shipping companies, to anyone who's interested in avoiding whales, and push that information out to help do conservation activities. So now that I've given you a taste of what we're expecting, sort of what's next for the agency, and this is a slide that will overwhelm you and it overwhelms you in ways that you may not even realize. So this list in this kind of lightish color, those are all of the satellites put up by NASA, again, many with international and interagency partners that are looking at Earth for Earth science. I think that's amazing. All of the yellow ones are the ones that we have coming up in the next decade. And that's even more phenomenal. And so what we're doing is looking at developing higher spatial resolution information, higher temporal resolution, and connecting that with previous satellites so that we can develop this long, scientifically consistent record. But we're also making new kinds of observations. That's part of the more of what's coming next. And so many of you who were at the opening plenary saw the talk from the International Space Station. And we use that International Space Station as an Earth observing platform. And one of the instruments that's going to be going up there is called JEDI. And that's in collaboration with the University of Maryland. And they're basically, as JEDI, you might guess there is a Star Wars connection, they are shooting lasers from space to look at vegetation. And so on the ISS, they can send out active information in the form of LiDAR, and then get a measurement, a 3D vertical structure of what forests look like. And so you can imagine how this revolutionizes our ability not just to look horizontally across the Earth's surface in 2 dimensions, but really add that 3rd dimension. So you can understand forest degradation. You can understand why birds and frogs and other species are using specific areas and why, and get this better understanding. Another instrument that's going to be going up on the International Space Station is an instrument called EcoStress that's looking at the effects of drought on natural ecosystems as well as agricultural systems, and getting a better sense of how water stress affects vegetation productivity, which is going to be particularly important in the light of climate change. We have other satellites. We have NISAR, which is an active radar mission that's in collaboration with the Indian Space Research Organization, ISRO. And so this is just giving us an amazing wealth of observations. But as part of this overwhelming amount of data, I like to say that scientists have a love affair with data. We always want more of it, but we get a little overwhelmed because there's a lot of it and we don't know how to process it. And so one of the uninteresting looking things, but very important things we're doing is developing an onboard processors that help process the data on satellites to help get it back to Earth, because we're collecting more and more and more data. But if we don't get it back down to Earth and get it out to people quickly in a format that's usable, it's not as great as it could be. So NASA has about 19 terabytes of Earth observing data in its records right now, and we add, I think, something like 12 terabytes a day. Just for reference, 19 terabytes. The Library of Congress, if you digitized it, would be about 10 terabytes of data. So that's an amazing amount of information. And so what we're also looking to do is help develop more analysis-ready data and what we call higher-level products. And so this is a way to get information to you, the biodiversity research and conservation community, in formats where you don't have to be an expert in remote sensing science in order to use that information for your own purposes. And so by working with our international partners, we can identify ways to develop these products that are really useful for you and where you can take your conservation expertise. And just as another plug for NASA, all of our data are free and open access. So anyone at any time can come in and download any of our data to do any kind of research or applications that they want. And so we're really interested in hearing from this community about what is it you want. And that's part of my job at NASA is I work with conservation NGOs. I work with our international partners to get a better understanding of what are your science needs so we can help tailor our research efforts for that. So we have a lot of exciting stuff coming up. We've done a lot of great work, and I'm happy to answer any questions later on, or we have somewhere in the back, someone found them finally, some NASA brochures about remote sensing. And so hopefully we'll pull them out if you want to get some more information about remote sensing itself, or if you want to hear some more conservation stories that NASA has helped support. Thank you.